So, even, in today, many engineers are cutting records made from digital files, right? It's very common. So then one would ask, well, how does the digital file or the CD sound against the record? And I don't know why, but the records sound better. I don't know why. Now, I've got a hypothesis. I don't know that it's grounded in anything, so please don't take what I have to say here. Please don't take what I have to say here with any level of certitude, okay? The human ear is extraordinarily sensitive to timing. When audiophiles get together, they might talk about their sensitivity and frequency. Yeah, I can hear up to so-and-so frequency, ba, 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 ba. Well, they forget that there's this thing called time as well. We're extraordinarily sensitive to time. Don't let me forget I want to go back to a little story on the development of a particular turntable called the OMA when it comes to time, okay? Please remind me.
Yeah.
Our sensitivity and timing is really important, and something that on an evolutionary basis we've developed, so that when we're walking through the savannah or the woods and we hear a twig break, let's say, right, we can quickly say, oh, it came from over there, right? Well, that's because in the frequencies that most natural behaviors occur, like twigs breaking, and we're talking 1,000 cycles to about 5,000 cycles where we're most sensitive. The difference in time that it takes for that signal to reach this ear versus this ear, a matter of single-digit milliseconds, we can hear, right? Our brain can process that and say, oh, it came from there, because it can sense that difference in time. Now,
JR, may I interrupt here a little bit?
Yes.
Well, I'll just like to add to that. The whole reason for that, what you're saying being true, is from an evolutionary point of view, is that human beings have evolved to sense timing and direction to fight as a survival instinct.
Of course.
We have learned to sense where danger is coming from based on timing, where the sound is coming from.
Yes,
that's how human beings have evolved.
If we hadn't evolved with that ability to identify potential danger, we may not be here today, right?
Exactly.
Yes. Yeah, it was a necessary evolutionary adaptation to avoid danger, because we certainly weren't the strongest beasts in the kingdom, right?
Exactly.
Yeah. So then the question becomes, well, with digital, of course, what it is we're sampling very rapidly the musical signal and breaking up into very discrete portions, storing that data in discrete portions, and then reassembling, right? Now when we reassemble, even at 44,000 times per second and on up, here's a question. This isn't any level of certainty. Are we sensitive to the fact that this is not a continuous signal? When we cut, and if the answer is yes, then if the answer is yes, and somehow we sense that it isn't quite as realistic as if it were a full-on analog reproduction, then when we use a digital file to cut to the lathe, well, the lathe is, as it carves out the groove and makes the undulations, it's going to make a very smooth transition to the next bit of information, right? It is by nature going to, it won't work in those discrete portions, right? It'll just transfer, it's moving, right? So it can't stop right here, disappear, and show up over there, right? It will travel there. Meanwhile, it's cutting. I guess I should limit how much I'm going to say on this, because I don't know, and it hasn't been fully studied. Now I'll get to the OMA thing. Okay, the
Okay.
OMA turntable.
That's the term.
Because it
JR,
goes into
JR,
this,
one moment. JR, one
yeah.
moment. There's one question which I think is relevant to the topic at hand. So Srijesh is asking a question. Isn't the I think it's ITD stands for inter-oral time difference. Is that right? So he's asking, isn't the inter-oral time difference only valid for frequency up to 4 kilohertz or so? Or is it above that in level? Like that's the question. Srijesh, I hope I got your question right. You might want to unmute yourself and ask if the question directly if there's anything else that you want to add.
Yeah, I actually have a bad voice, which was why I was typing. My question was, intraoral time difference is mostly valid until 4K. I mean, there are debates between 1.5 and 4K, and above that, it is definitely intraoral level differences. So when we talk about timing in terms of like when we're talking about staging, transients don't usually fall in this region. My understanding is they're above this, so I was just curious about that part.
Okay, so this is outside of my level of expertise, where these limits are. I do know that in frequency, certainly the human ear is most sensitive, and that's what the Fletcher-Munson curve is all about, from about 1.5K to about 5K. And that a lot of the studies on time, that the ability to hear time differential, let's say between two tones, both of them a few milliseconds long, and and some multiple apart from each other, really fast, we're done at a higher frequency, somewhere around 1,000 kilohertz or something. So I don't think I'll be able to answer that question with any level of expertise. I'm just trying to lay out the case that the human ear is incredibly sensitive to time as well as frequency, right? And so you could be right, Srajesh. Okay. And so the OMA turntable, this was a Herculean effort in development. There's a fella, OMA is out of New York State, or Pennsylvania, depending where you wanted to say the
Yeah,
factory.
it's I think New York State, JR. It's Oswald Mills Audio, right? That's right.
Oswald Mills Audio, correct. Yeah.
Yeah.
They worked with a pneumatic engineer out of New Zealand named Richard Krebs. And they contracted Richard to make the best turntable he could possibly make. And then they employed the help of engineering students at Bucknell University to do finite element analysis and so forth. But one of the things that as they were developing one of the mandates was that it would have to be direct drive. Okay.
Oh.
And direct drive turntables have really gotten a lot better now than they used to be, largely because of digital technology, right? Which is to say the motor control part of this, the side, right?
Motor drive.
The one of the things they had to manage, and they were using this motor that apparently was made by a company for which the cheapest product that motor is used in was $8 million. It was mostly used in defense and aerospace and such, but they were using this incredible motor.
Once again, I'm very sorry to interrupt here. So the particular topic that you're discussing is right up my alley in my past background experiences. So we'll probably cover on this in future sessions, because the direct drive system and let's say a geared system is a very, very interesting topic, and probably in the turntable space, the direct drive as opposed to, let's say, a belt drive system, and how, as you correctly mentioned, the evolution of direct drives, and it's getting just better and better. It's a very, very interesting concept, and I think it calls for a separate session altogether. We'll probably cover more on this in a future session. It's a very, very interesting topic that I would love to participate in myself. Yeah.
Yes. Yeah.
Back to you.
So as they're working on this motor, of course, it's easy. It's relatively easy to generate a constant 33 1/3 RPM, right? The question becomes, how often are you sampling for that 33 1/3 RPM? If you're sampling, longer time durations and making a longer average, it's easier to hit it. right? But especially when you've got things like stylus drag, then the question becomes, well, at what level of discretization is there any audible benefit for us to be sampling the speed and then correcting for it, right? So they convened a listening panel to help answer this and other development questions. And so while they had their programmer programming the level of discretization with which the sampling and correcting was being done, the panel was being asked, okay, we made a change. Is it better, same, or worse? Right? They got down to sampling and correction to the arc-second level.
Oh.
And the panel could still hear it. And there are 1.29 million arc seconds in one revolution.
Whoa.
This means that at 33 1/3 RPM, that's 770,000 times sampling.
Oh,
Higher than that at 45 RPM.
right.
And this panel could hear the improvement. Okay, sampling at that level, and this is just rotational speed. It's just amazing that they were sensitive. The panel unanimously could say we could hear it. And what were they hearing? Better drive and transient impact, right? That's how they experienced it. It sounded more punchy. The pluck was more true and nice and sharp. You know, if you listen to unamplified instrumentation, and you're up relatively close, just like the microphone is up relatively close.
Right. So the amplifier.
The pluck of a string or the strike of a drumstick on a drum head or a rim shot, that initial transient is really sharp, right? And that there's a lot of realism to be had there. And most stereos have, and acoustic environments for that matter, haven't been attended to well enough to make that initial transient attack realistic, right? So it's just another thing that we chase, that initial transient. It's addictive once you have it. So, oh God, I don't want to give that away, right? Just makes it sound real. But isn't that remarkable, huh? 770,000 times sampling at 33 1/3.
So then how does this, how do you solve this problem in the real world? I mean, are you guys sampling at that rate and correcting for speed, or just using a damper in the shape of a belt and kind of?
Yeah, no, good question. And I don't have the answer. Every designer does something a little bit differently, right?
Okay.
And yeah, in the case of belt drive, the belt itself is it's a filter, right? And that filter is there to help filter out speed variations, right? And wow. But so every designer does it differently. And you know, I'm not a turntable designer. I spend plenty of time talking to them and mutually learning from each other. You know, my area of expertise is certainly in the how to optimize the transcription. Once the equipment's been made for you, how do you optimize what you have, right?
So your company does not look into the problem of speed optimization.
No, we have not looked into that problem of speed optimization. There's still so much that's been unstudied on the alignment side.
Oh, okay.
Not everything has been studied. I mean, we are in our second year of gathering data for the expected publication, or at least submission. Publication's not up to me. Submission of a paper on something called zenith error, which has never been studied, principally because fine line contact style weren't common in the heyday of the 60s and 70s and the early 80s, when vinyl transcription was being studied, right? So the other, I mentioned before why I'm so optimistic, and why in that video that is available to view, it's actually on my website, of that panel in Munich. I only gave you one reason why I'm so optimistic about the future of analog. And that first answer was computational and analytical powers, right? To be able to understand what's going on with the system and find areas to improve. But the other is the population hasn't even employed the basics. I mean, and that's part of what my analog evangelism has been about. I'm going out and say, listen, what we have thought we knew about things like VTA and SRA, which is vertical tracking angle, and stylus rake angle, what we thought we knew about cantilever alignment, it was either incomplete or wrong, right?
Mhm.
And so with the studies that we've been working on, been able to find a way for people to manage these variables on their own. So remember, I mentioned there are 7 alignment parameters: 1 linear dimension, 2 forces, and 4 angles. So, we know how the record was cut. We know what the shape of the tool was. We know what the engineers were aiming at with regards to their 4 angles. So let's take a parametric approach on playback to hit those 4 angles and to manage those forces in that linear dimension, right? So it's not, people thought, well, why don't we just, read the electrical output from a test record to tell us, to look at the distortions and then improve for distortions. And while this is a sensible course of action, it's so far has been very unrealistic. And part of and this is why this goes to the very reason why we're so late in submitting our paper on zenith error. Because first we started on zenith error, and let me just, for those who don't know what zenith error is, okay, so here is a 1000 to 1 scale model of a fine line contact stylus, okay? Now, if my arm is the cantilever and I point the stylus right into the camera, so the camera is at its zenith.
Oh, okay.
The camera is at its zenith. Now you will note, I'm trying to get properly oriented, note my arm, which is the cantilever, right? Now, when we align the cantilever, it's only a proxy. It's only a proxy for what actually matters. What actually matters is if you were to draw a line between the left channel contact point and the right channel contact point. If you draw a line, we're assuming that it's perpendicular on a horizontal plane to this cantilever. But there are 3 manufacturers in the world of stylus and cantilever assemblies. 3 for the high-end market. And they should be offered tolerances with which the accuracy with which they mount this to this. And the zenith error is this, okay? The degree to which that line that I just showed you is not perpendicular. Their tolerance errors are plus minus 5 degrees, which is huge, particularly since we spend so much time aligning the cantilever, which we can do to, I know that I can do to within a half a degree accuracy. I've been tested for that. But there's plenty of other people who can do just that. There's nothing special about that. I've just taken the time to be good at it. And when a stylus cantilever assembly does have the zenith error, let's say 5 degrees, it doesn't sound the same. Now, it doesn't sound bad either. In fact, it's the type of error of omission that you wouldn't even notice, right? You wouldn't notice until it's been fixed. And then once it's been fixed, you get significantly greater clarity, instrument separation, transient attack. Most people live with this to some degree and will never know. I've seen as much as 17.5 degrees in a $4,000 cartridge, seen multiple $10,000 cartridges over 10 degrees. Yeah, and the amount of money you pay for a cartridge has no relationship to how well this has been mounted to the cantilever. Not at all. Unfortunately, it gets sloppier. Why does it get sloppier with the more expensive cartridges? Because the
So
more
JR,
expensive
I'm sorry to interrupt. JR, I'm sorry to interrupt at this
Yeah.
point. So it begs a question. Like we have standards, let's say some data which has to be presented in the case of amplifiers or side speakers, like so some standard set of data. Don't we have standard set of data for cartridges and tone arms, like which ought to have probably like minimum set of standards to be followed?
Yes, yes. So yes, there are, and some of them have been even updated in 2020 in IEC, the IEC standards. But the manufacturers of these stylus cantilever assemblies, they have their standards, and you can go online and at least one of them see what those tolerances are, right? There is a lot of slop, and a lot of the standards as well aren't actually being, as I mentioned before, some of the standards aren't being respected by the cartridge manufacturers. You know, we've analyzed several hundred cartridges now, and we database all of them for their angles and see how they're doing. And there's a lot of slop in the industry now, in part because the consumer hasn't learned how to identify it and do something about it. So it's a lack of demand because we're kind of ignorant. Well, that's why we're here, right? Right. And so we've made some people in the cartridge industry uncomfortable, no doubt, right? Because we're pointing out that in some cases the emperor doesn't have any clothes, right?